then yaprak, then les, then Moses, Yinping, Shu Xian, Su Zhen.
You can hear me?
Yeah.
Okay, great. Cool. Okay. So this question is homework ahead. It's the fifth homework, and um, so basically you want to read the question. The question is asking you to find a
Oh, hold on,
population.
hold on. Hold on a second. This is 5-3. Oh,
Yeah,
hold on a
question.
second. Oh, okay, that's okay. 5-3. Yeah, go ahead, Christian.
Okay. So this question is asking you. The main idea is asking you about a population over time, and with the information that it gives you, such as the birth rate and the death rate, what you can interpret the information as is as dp. Wait, let me get my great. You can interpret it as dp over dt is equal to your birth rate, which is signified by beta, and your death rate, uh, signified by delta, both of those subtracted by one another, multiplied by your population. And with this in mind, and we have a formula, what we can do is basically find out what our birth rate and what our death rate is, and then further simplify it so that we can find a general solution to it. But let's just start from the beginning and find the birth and death rate. So first I found the birth rate and the death rate. I did that by just reading the question. The question says P of t has a birth rate of 0. Shoot. Ah, erase
It's
that.
okay.
Sorry.
It's okay.
Uh, so P of t, okay, got it, has a birth rate of 0. So my birth rate right here is 0. And then it says that the death rate is proportional by 1 over the cube root of p, which is right here. We don't know what our death rate is exactly, so we just have b as the constant, and we multiply it by 1 over cube root of p because that's the proportionality to the death rate. And once we have our birth and death rate, we sub it into our equation, and we get that dp over dt is equal to negative b over um, 3, I mean, over the cube root of p times p. And then after that, we simplify, okay? We factor out the negative b, and then we have p over uh, 3, oh my God, over the cube root of p, and then we just use exponent laws. With that in mind, we get, after we simplify it, subtracting 1 from, no, yeah, 1 subtracted by 1/3, and we get 2 over 3. After that, we have dp over dt is equal to, once I put it back into root form, negative b multiplied by the cube root of p squared. With that, what we're going to do is separate the variables. I separated the variables by multiplying by 1 over the cube root of p squared on both sides. After I did that, I then again multiply by another term, which is dt on both sides. And then I integrated both sides. In integrating both sides, I got negative b t plus c. And on the left side, I got the cube root of p. And then after that, I divided both sides by 3. Well, actually, no. The left side, I got 3 multiplied by the cube root of p. But yeah, I multiplied by 3 so I could get rid of the 3 on this side and then transfer it to the right side. And then I'm left with, uh, and then I'm left with, okay, yeah, the cube root of p. And then oh my God, no. I raise each side to the power of 3. And then I cancel out the cube root of p for the left side, and then I just cube the right side because I have to, so I can isolate p. And then I have P is equal to this right here. P is equal to negative BT over 3 plus C over 3 raised to the third power. And to further simplify this general solution that I found right here, I substituted negative B with K. And it comes into play when I go back up here to the second part, in which I have to find my C and find my K for my general solution. I did that by using the value of the population at time 0. So I use that the population of mice is 1,000 at time 0, and I substituted for P of T. I put 1,000, and then I plugged in 0 for all of my T's right here, which is just 1T really. So that becomes 0, and I just have 1,000 is equal to C over 3 cubed. I cube root each side, and then I'm left with 1,000. I'm left with 10 is equal to C over 3, multiply each side by 3, and then I get C is equal to 30. So I found one constant for my general solution right here, find the other constant, which is K. And in doing that, we use the population after 3 months. So we know the population is 216 after 3 months. Okay, so I plug in 216 for the population P of T, and I then plug in 3 for the time, right? And then I further isolate K by cube rooting both sides, and then I'm left with 6 is equal to K plus 10, subtract 10 on both sides, and then I get negative 4 is equal to K, which is another constant. We found 2 of our constants, and all we have to do is bring everything together. We got our general solution and 2 of our constants, our K and our C, and in doing so, we get this equation right here. Shoot, damn it. I hate that. But that's the equation right there, okay? Yeah. So after that, what we want to do is that we want to find out what the population is equal to at 0. We found the equation. We got most of it out the way. We just did the easy part. Substitute in 0, and then we get 0 because the cube root, nothing really changes. It's still 0. And it's equal to a negative 4 over 3 plus 10. Subtract 10 on both sides. And then we have to, oh yeah, multiply. Sorry, this confused me. The T looked like a plus for a second. Multiply the inverse right here. And then we get on both sides, and then we get 7.5 is equal to T. So in 7.5 months, the population of mice is equal to 0 for this question. And yeah, so that's the answer, 7.5. Yeah.
Okay, so hold on a second. Let me understand. I think you're missing T in your general solution. Oh, no.
Oh, no, T's right here.
In the second line. That's okay. That's okay. Because your plus and T is a difficult to tell. But it's great. Good job.
Mm-hmm.
Good job on solving this question. All right, great. Ryan has a question?
Oh, wait.
Not for Christian. I just wanted to ask, since my question is fairly similar because it's from the same homework.
Okay.
It might be a good idea to have them next to each other because it's
Okay.
sort of Christian solved for the constants, and in my case the constants are given. The rates are given.
Okay. Okay. Go ahead. Go ahead. All right. Les, you have a question?
Does Liz want to ask the question before I start, or?
Yeah, Liz raised her hand. Liz, I cannot hear you.
Can you hear me?
Yeah, now.
I wanted to say I wanted to present like the same question, which is 5.3, but I got like a different answer. I don't know if I can still present.
Oh, so it's not similar to Christian's
It's the same
solution.
question, yes, but we got different answers.
Oh, okay. So maybe let's see yours first. Then Ryan. Okay, Ryan.
No problem.
Okay, thank you.
Okay, thank
Yeah,
you.
you're welcome.
Um, I think we would. Can you see my picture?
Yeah, I'm trying to make it larger. Yes.
Like I think we would like the one we just did. We have a population of mine, which is P of t, has a birth rate of 0 and death rate proportional to 1 over cube root of p. And if at time 0 the population of mice is 1,000, the population is 216 after 3 months. When will the population equals to 0? So like the previous presenter said, we're gonna model this problem over this equation, which is population change with respect to times equals to birth rate minus death rate time population. We know that the birth rate is equals to 0 and like the death rate is proportional to 1 over square root of cube root of p, which can also be rewrite as 1 over p exponent 1/3 or p exponent minus 1/3. So that rate is equal to k, which is a constant of variation times p exponent minus 1/3. So we're gonna, since we have the birth rate, we have the death rate, we're gonna go ahead and replace that into the equation that we had. So dp over dt equals 0 minus k over p exponent 1/3. dp equal over dt equals minus k times p exponent minus 1/3. We cross multiply. dp equals minus k exponent p minus k times p exponent minus 1/3 dt, and we divide both sides by p exponent minus 1/3, so we can have like dp and p on the same side. We end up with p exponent 1/3 times dp equals to minus k times dt. So this is gonna be like our differential equation. We also have like two condition when the population at t0 is 1,000, so p of 0 equals 1,000, and after 3 months is 216, so p of 3 equals 216. So we're gonna solve the differential equation by integrating both sides. We integrate p exponent 1/3, we have p exponent 4 over 3 divided by 4 over 3, and we integrate minus k, that's give us minus kt plus c. So we're gonna now apply the initial condition. We start with when t equals 0 and p equals to 1,000, so we go ahead and we replace. So when we replace that into the equation, we find that c is equals to 7,500. Now we're gonna use the second condition, which is p of 3 equals to 216, to find our other constant, which is k. So we replace P by 216 and we replace T by 3. So when we solve, we find that K is equals to 2176. So we can finally find, now we have C and we have K, we can finally find the population, at what time the population will be equals to 0. We replace P by 0, we replace K by its value, and we replace C by its value. When we solve, we find that C is equals to 3.5 months. So the population of mice will be 0 after 3.5 months.
So interesting. Okay, so where what's the difference between you two? Why made the difference?
Yes, I don't know where the mistake
Difference
come
is
from. I don't know it's from
much.
mine or
Christian has 7.5 months. You have 3.5 months, and also your value for K and C are different. Your K, yeah, your C is 7,500. I don't know. I cannot tell. I cannot tell, you know, who made a mistake right away. But very similar. Okay, very similar.
yeah,
So yours,
maybe it's a problem of calculation. I don't know.
yeah, unless we put it side by side, we can tell. But okay, that's okay. All right. Okay, Ryan, your turn. By the way, if the rest of you didn't go to you know, lecture 5, so they all choose lecture 5 to do it because that's not enough question. I didn't make enough question for you guys to pick. So Christian and Liz and Ryan also went ahead of the class. All right. Yes, Ryan, please.
So I did question 5.4, which is fairly similar. It's actually quite similar to one in the text. The numbers are just slightly different. So we have a population of squirrels represented by P of T, and that satisfies the logistic equation given here. And this is a standard logistic equation where A times P is the absolute birth rate, and B of P is B squared is the absolute death rate. And of course, dt over dt is the overall rate of their growth or decline. And so at time t equals 0, the population, which I'm going to use P0, and that's 120. And at least the way I'm reading this, still at time t equals 0, there are 4 births per month and 3 deaths per month. So 3 squirrels did not get their daily intake of nuts and dropped dead. How many months does it take for the population to reach 95% of the limiting population? So depending on how you look at it, limiting population could either be when they all die out or when there's too many of them for the environment to handle. I think in this case, it's there's too many of them. So that's also called the carrying capacity in some cases. And so we have the initial birth and death rates, which are 4 and 3 respectively. And to solve for the rates, we basically take the initial rate, that's basically just how I wrote it, equals A, so that's from here, times the initial population. And we take the death rate, which equals B times the initial population squared. And so basically we have an initial population of 120 squirrels, and we have an initial birth rate of 4. And so we just solve for A and we get 1 over 30. Doing the same for B with 3, and we get 1 over 4,800. to find the limiting population value, we actually take A over B, and that's 160. And the reasoning behind that is the squirrels are dying for a reason, probably the surroundings. So the surroundings are going to limit the birth and death rate to some extent. So 160 is the full limit. And so when we take, when we solve this differential equation, we get this monstrosity, and there's something like 3 pages with how to calculate that, including a partial fraction decomposition. I didn't do that here since I'm sure Professor Chen will cover it soon. So I basically just stole the formula and plugged in the numbers. And so we have a K here, which Christian and Liz, I believe Liz showed. And so in this case, our K is actually going to be the B. So this one right here, the death rate. And so we basically want 95% of the limiting population. So that's 0.95 times M. I left that as M for a good reason, you'll see. And then initial population times M again. As you can see, these two cancel out. Then we have initial population plus carrying capacity minus the initial population times e to the negative rate times the limiting times the carrying capacity times t. And so in this case, we're solving for t. When are we going to reach 0.95% of the limiting population value? And so that's basically what I did here. 160 minus 120 is 40. And multiply that to the other side. Then just divide both sides by 0.95. Then subtract 120. Then we're left with this, what we divide by 40. And now we take the logarithm of both sides. Of course, the exponent comes down. And we're left with negative t over 30 times ln of e. This is obviously 2 inverses, becomes 1. And then the ln of 3 over 19 can be written like this. Then solving from there, multiply both sides by 30, well, rather negative 30. And here we have t equals 30 times ln of 19 minus ln of 3, or approximately 55.37 marks.
Great.
Thank you.
All right. You're welcome. Great. Because I like this. You know why? Because study, you know, you have elementary school, middle school, high school, college, in the future, maybe graduate school, maybe PhD programs. In the end, what counts is the ability to study by one's own. Especially if you go with higher education for PhD, you know, you study by yourself all the time. So education in the end is the ability to study on your own, on one's own. I like this. So Christian, Liz, and Ryan, you know, show us, you know, we are able to study on our own. Great. All right, let's see now. Yaprak 4.3, the Moises 8, Yinping 7, Shuxian 1, Suzanne 3. Yaprak, are you here?
Yeah, I am. It's loading.
Okay.
I think you guys are seeing it, right?
Yes.
Okay. So I'm presenting question 3 from homework 4. So right away, we can see that the given equation is in this form, right here. So we want to check if m of y and nx are equivalent, meaning we want to check if they're exact or not. And after calculating it, I see that they're exact. So this means that mxy plus nxy.
Hold on one second.
Yeah.
I think this is oh, I'm sorry. This is question 3.
Yeah.
Very similar to question 2, huh?
Yeah, I think it's very similar. But question 2 was like question 2 had like cosine and ln x in it.
Oh, I see. Okay. Yeah, go ahead.
So after finding that they're exact, we can see that we can use this method to solve it. So to find fxy, I take the integral of f of x dx, and our f of x is just mxy, and that was the x cubed plus y over x. So I take the integral of that, and I got this. And then instead of adding a constant, I added a additional function here. And then later on, we need to calculate f of y. And to do that...
Hold on a second. I think that's a mistake here. Hold on. So you're integrating in x direction, right? I'm not sure if you can see my circling.
Yeah, that's y over x.
Right, that's y over x, right? So you are integrating y over x in x direction, right?
Yeah.
How do you integrate that? How do you get a y times x squared divided by 2?
Yeah.
That's a mistake. Because your
Yeah,
y is
sorry.
constant, right? Your y is
Yeah,
constant.
it is.
You're
So we move
integrating
that
y
out.
over x.
Yeah.
I'm sorry?
So that's why we moved y to the out of the integral, since it's a constant.
Your screen is gone.
Oh, sorry. Sorry.
It's okay. No, can you make a corrections here?
Yeah.
So this is wrong integration. Let me highlight for you. This is wrong integration for this in x direction.
Mm-hmm.
Can you make the corrections now?
Yeah, sure.
Just think about this. Think about it. You integrate because the y is constant. You can leave outside.
Yeah.
You have
So that's both sides.
Yeah, you have 1 over x dx. So
Oh, yeah, it's ln x. I'm sorry.
that's
Yeah.
right. Okay. Yeah.
Sorry.
It's okay. So that's a mistake. Okay. Yeah, keep going.
Okay. It was ln x. And then to find f of y, we differentiate this whole thing with respect to y, and then we treated x as a constant. So yeah, so it's x squared over 2 plus g prime of y, and then f of y is basically y squared plus ln x. So we had this equation here to solve for g of
You have to
y.
change this. You have to change this.
Yeah.
You have to change this one, right?
Mm-hmm.
You already made the correction, right? So keep making corrections.
Mm-hmm. So it's just y.
Okay, hold on a second. Oh, hold on. Okay, so this is where does this Fy come from? Fy come from you're taking derivative of this term, right?
Yeah. And Fy
Okay.
is nxy, like here. This one is f of x.
But this term already changed, right? You see, you changed it to be lnx, right?
Yeah.
So you have to keep changing it.
Yeah. So when differentiating with respect to y, it's not that. It's y squared over 2.
No, you're not integrating. You're taking derivatives.
I'm sorry. I messed up. I got confused. I'm sorry.
That's okay. Okay. So no more x squared over 2. X squared over 2 is ln x, the correction you have made. Now you're
Yeah,
taking
that's it.
derivative with this, right? In terms of
Yeah.
y. So the first term, of course, becomes 0.
So it's 1 over x.
You don't have
right?
1 over x. You ln x, because your term is y ln x. And you differentiate with y. So differentiation y just 1 times ln x. So your x squared divided by 2 is just ln x. So it should be fy should be ln x plus g prime y, right?
Mm-hmm.
Okay, keep going then.
Okay. So this here is also ln x. And after that, so I rearranged the equation. I got g prime of y equals y squared ln x minus ln x, and then I integrated both sides.
No
and then
more. No more ln x, right? Because on both sides of the equation, you have ln x. That cancels
So
out.
it gets canceled out, yeah. And
Right.
then it's just y squared. Then we don't have this. And then, yeah, so g of y is this. And then we plug it in here to find fxy. And then it's, so yeah, so this is the answer, I guess. I should have realized it before. I'm sorry.
Right. But just if you can make corrections here, you know, I still count it as a presentation. Just justify something else. Just keep making. You're almost done. Just making corrections. Just making corrections on this line. Then you'll be done with it.
Okay, so fxy is x to the 4th over 4 plus, hold on a second. Yeah, plus y times x squared over 2 plus
You don't have
y
this
cubed
anymore.
over 3.
You don't have this anymore.
But
Remember,
comes
that's
from,
a mistake you have made. Oh,
yeah, sorry.
Yeah, that's a
But that
mistake you have.
was, oh yeah, so that's ln x.
That's right.
Yeah.
Okay,
Yeah,
so tell us the final answer.
And the final answer is x to the 4th over 4 plus ln x plus y cubed over 3.
And then plus a constant, right?
Yeah, plus a constant, but I combined c of 2 and c of 1 here because
Right.
it's I mean, yeah, they're constant, so we can combine them.
Right, that's the
And
last
then I
step.
call it c sub 3.
Right, treating as a level set. Okay, great.
I'm
All right,
sorry
so
for the mistake.
Yeah, okay. You know, we always make mistakes. The important thing is we're able to make corrections over our mistakes. All right. Okay, good.
Thank you.
Good. All right, next, Moises, then Yinping, then Moises, then Yinping. then Shuxian, then Suzanne.
Can you see the screen?
Yeah.
Okay. So I started off by substituting y prime with p of x, and so
Remind us of the question.
excuse me?
Always start with the question itself. Always
Oh,
start, always remind us
okay.
of the question itself.
So the question is x squared times y double prime plus 4x times y prime equals to 1.
That's not the
And
problem. That's the given equation.
oh, the problem is it just wants the general solution, sorry.
Okay, for this given
For
equation.
this given equation, yes.
Okay.
And so I began by substituting the y prime with p of x, meaning that the y double prime would be equal to p prime of x. And so I just substituted back into the original equation, and I divided x squared on the whole equation so I could leave p prime alone. So it looks like a first order linear differential equation. So I could solve it that way. And so I made it in the form of dy dx over dx plus p of x y equals to q of x. But in this case, my y is going to be a p of x and my dy over dx is going to be a p prime of x. So for that, I have to find the integrating factor, which in my case, it would be e to the power of the integral of 4 over x dx, which resulted into x squared. That would be my integrating factor. So with that, I have to multiply back into my original, no, not original equation, but my equation of p prime x plus 4 over x px equals to 1 over x squared, which gives me x to the fourth times p prime x plus 4x cubed p of x equals to x squared. And we know that the derivative of the integrating factor times y equals to the integrating factors times q of x. But in my case, again, my y is my p of x, so I replaced the y with the p of x. And to solve for my p of x, I have to integrate on both sides. So I did. And it gave me the new formula of x to the fourth times p of x equals to x cubed over 3 plus a constant, which I just named c1. And so I isolated p of x, giving me the equation 1 over 3x plus 1 over x to the fourth times a constant. And the second step, we know that my p of x is actually equals to y prime. And we want to know the general solution of the equation. So we have to solve for y, and we have y prime, so we can just integrate the whole equation. And so we get 1 over, well, we integrate both sides, sorry. And so we get 1 over 3 times ln of x minus 1 over 3 x cubed c1 plus c2, because we have two constants because we integrated twice.
Great. Yeah, this is another kind of solving equations using substitution to deal with higher order of derivatives, which is each time we just substitute with a variable. Yeah. Okay. Great.
Thank you.
Okay. That's more. Is in pin 7. Oh.
Sorry, give me 1 second.
Okay.
Can you see my screen?
Yeah.
Okay. My question is 7. Is y double prime equals to y prime to y prime to the square, and we're missing x, so we solve the x. Let px equal y prime, then we have dp dx equal to dp over dy times dy over dx equal to p times dp over dy. Then we have the p times dp over dy equals to 2 times p to the square. And 1 over p equals to dp dy equals to 2. And we
Hold on. Okay.
uh,
Yes. Yes, go ahead.
Okay, we move the dy to the right side and integral both sides. We get lnp plus c1 equals to 2y plus c2. lnp equals to 2y plus c3. We use e to get p equals to e to the 2y times e to the c3, and we have p. Since e to the c3 is also a constant, so we have p equals to c4 times e to the 2y. And since p equals to dy dx, we have dy dx equal to c4 times e to the 2y. Move e to the 2y to the left side and integral both sides. We can use the Euler substitution to get the negative 1 over 2 times e to the negative 2y plus c5 equals to c4 times x. Then e to the negative 2y equals to negative 2 times c4x minus c5. E to the 2y negative 2y equals to negative 2 c4x plus c5 c6. Since negative 2 times negative c5 is also constant, so we have the x equals to e to the negative 2y minus c3 over negative 2 times c4.
That's your solution?
Yeah.
X equals to some y?
Yeah.
Okay.
I saw the
okay.
notebook is
as long as it's an equation. Okay, next time when you do your presentation, explain what's going on. Explain why you do what you did, and it's not only reading what's written there. Okay.
okay.
All right. Thank you. Su Xian, then Suzanne.
Yes. Let me loading. I hope I can find it. Hold on.
Okay, for the rest of you, because so far the presenters are the presenters. It's like every class they are presenting. What about the rest of you? How are you going to get the 30% of your grades from presentation? And Liz reminded me I may not have enough questions for everyone. So this is a modification. All right. So while Su Xian is trying to find it, let me share with you.
Oh, could you see it?
What you could do is, okay, just hold on, Su Xian.
Okay.
What you could do is, let's see, 3, 4. So I may have enough questions for you. So what you can do is this. You just change the number. All right. Just change the number. You see here, 2, 3, 4, 5. That's just some numbers, right? You can make 6, 7, 8, 9, 10. All All right, you can just you can just change those numbers to make more questions about it. Yes, Gregory.
Professor, are you showing the questions on the screen now?
I'm not showing questions. I'm just showing the homework set.
Oh, okay.
Oh, okay. Like you didn't see that when I click.
No.
Okay, let me just repeat myself. I mean, that makes sense. So let's see, any question, right? Any homework set doesn't have enough questions. And maybe you guys are talking, right? Someone already picked up to present. So what you can do is you just change the numbers in the question to make it extra. Let's say the homework set only have 6 questions. You can make a number 7 for yourself. Okay, this is my number 7 homework. I have changed some numbers. All right. Okay, Sushan.
Yeah.
Are you ready?
Could you see it?
Yes.
Okay. Thank you. My question is find the general solution by giving the 2x squared minus 3y squared dx plus y squared minus 6xy dy equals 0. This one, so I step like a 5 and 6 step by myself. Okay. First of all, I suppose looking for and find out which one's m, which one's n. M is 2x squared minus 3y squared equal fs. And then the n is y squared minus 6xy equal fy. But if you says, okay, you need to know what is exactly, so you need to find out my is equal nx. So my is like a partial, like a m by partial like a y. So when you partial derivative 2x squared minus 3y squared, mean is 2x squared is constant is equal 0. So we just like a derivative negative 3y squared equal negative 6y. So nx same. So just treat y like a constant. So when I like a derivative negative 6xy equal negative 6y. So my equal nx. So I can use it. That's like an exact like an equation. So second steps, looking for fxy. So you can integral like a fx dx, or you can integral like fy dy. But I choose integral like fx dx. So when I integral 2x squared minus 3y squared dx, so first of all, I did a mistake. I crossed this. So correct answer is 2x cubed over 3 and minus 3x y squared plus, because I took like calculate 3, so I used to use xy. So I use xy instead, like qy, like a professor present. So this one is okay. 3 steps. So when I like did like a fxy, so I need to find out fy from the fx integral fx dx. So fy is from here. You can see the underlines when you like did like a fy. That's like partial y. So treat like x like constant. So x squared is 0 is negative 6xy plus xy pi, because you can see, okay, n is like a fy, so that's make equal. So I can find out like a xy equal y squared. Okay, and then I can integral like a constant xy, because, and then this y pi is y squared. So when you integral both sides, you can find the xy is like a y cubed over 3 plus constant c. Okay, you can see I have the arrow over there. So this is the x squared minus 3xy squared plus sy. Over there, I can imply sy, y cubed over 3c into here. We get the fxy equal x squared minus 3x y squared plus y cubed over 3 plus c. And then for the beginning is 0. Professor says the fxy can be like a c. So that's why. And then the potential equation is 2x cubed over 3 minus 3xy squared plus y cubed over 3 equals c. That's a general solution.
Okay, nice. Thank you. All right, I think Suzanne is the last one. Thank you. Suzanne is the last one. Question 3.
Yes, 1 second.
Oh, hold on. Yaprak already presented question 3, right? Yeah. Yaprak already did, unless you have different solutions.
Mine was like the mistake she like made, which we corrected in class. It was like with the same steps. I got x to the 4th over 4 plus y cube over 3 plus y ln x.
It's same as hers, right?
Yeah.
Okay. So please present the next class, all right?
Okay.
We'll choose a different question to present the next class. But thank you. All right. Anyone else like to present today? I worry about the rest of you. You're not presenting. Anyway. So 3 students already somehow taught us about population models. So this is one kind of application we use differential equations. And yesterday was 9/11. So horrible date to remember. And those people, they designed, the plane hits which floor. They did calculations, and they have scientists in their group. And those scientists, those mathematicians, knows differential equations very well. So in the future, maybe if you keep learning mathematics, you're learning something called a shock wave equation, a lot of different differential equations. And they found out one solution, and which, they did horrible things to human beings. Anyway, so this is one application we use for population models. Right? We could use for humans, we could use for animals, we could use for trees, we could use for plants. All right, so we already seen 3 students presented their work. Now let's just go over it. We have already seen one model for population growth. In that model, one assumes a constant rate of growth, which is proportional to the population size at time t, which is this, right? In here, k is a positive number. The general solution is something very dear to our eyes. Remember when we talk about the interest rate, something called compound continuously, right? It's a very low level mathematics class. Compound continuously, that's such equation. So this equation is a general solution for such differential equation. More generally, we could assume a birth rate, so beta of t, right? Beta is a function in terms of t, and the death rate, delta of t, where the rate of change in the population is given by, right? What is the differential? What is the differentiation? Differentiation is the rate of change in between of two variables. What is the dp dt over dt? Is the rate of change of p in terms of t. So that's beta of t minus the delta of t, the birth rate minus the death rate, and then multiply by p of t. What is p of t? You didn't say it, just population, okay? Just population function. The population function. Birth rate subtract the death rate. And if we compare this to this, so k just equals to birth rate subtract death rate. So k is a constant, we get the first population model. So birth and death rates can also depend on the size of the population, p of t. Right? So which means, you know, these two can be a function in terms of t, compositional functions. Notice that the birth and death rates are percentages of the population. For example, suppose the population is 500 at the time t, and the birth rate is 0.02, which is 2% per year. Then over the next year, there will be 0.02 times 500 equals to 10 births. Right? So this depends on the population. So the absolute birth rate for that year is 10. But the relative birth rate is the rate of, is just 2%. Let's see this example. Suppose a certain lake is stocked with fish and the birth and death rates are inversely proportional to this square root of p population p of t. At the time at t equals 0, p naught equals 100. So this is give us a point for this function. Right? So our initial value is given. And after 6 months, there are 169 fish. So we have two initial conditions. A, find a formula for the population. And B, find how many fish are there after 1 year. Right? So we're told that the death rate and the birth rate are inversely proportional to this. So the birth rate, beta, because the beta looks like a B, birth rate equals to some number, right? Like a scalar over square root of P. Why? Because it's inversely proportional. Well, you could think this is just A times 1 over square root of P. And the same thing for the death rate. Right? Delta looks like a D, so for death rate. Also inverse proportional to square root of P. Right? This B, this is a constant, multiplied by 1 over square root of P. So we use the formula dp dt equals to birth rate subtract death rate multiplied by the population function. That's the birth rate, that's the death rate, subtract. Right. You can simplify that to be this, A minus B square root of P. Then we can separate the equation, use the separable method. All these are just constant. So we integrate on both sides simultaneously. So left-hand side, we get a 2 square root of P. The right-hand side, we just get A minus B times T plus a constant. So we divide by 2 on both sides. We square both sides. We get a quadratic function. So the population function is just a quadratic function. So here we just let a constant, right? Because A minus B is constant. You know, instead of writing 2 variables, we just use 1 variable. We always, in mathematics, we always use these dummy variables because there's a huge, amount of variables we can use. Why we use a C1, C2, C3 in one equation, or A or B in one equation to represent different constants. We could just use one constant to represent the rest. Okay, so population is a quadratic function. Now we want to find our constants. We use the initial condition, right? Times 0, we have 100. We get C2 equals 10. We plug in C2. We plug in 10 for the constant term. We get a quadratic function, right? But we need to find the K because we want to because our population function is in times of T. So we want to find this K. We use the second initial condition, which is say 6 years later, the population is 169. So we plug in and we solve for K. In the end, we get a K equals to 1. All right, so we get our population function, quadratic function, right? And also is upward parabola, right? Upward parabola. Okay, now the second question is finding 1 year later, right? So a year later, how many fish? The population in 1 year. Well, 1 year equals 12 months. Equals 12 months. The units we use from the beginning are months, you see. 0 months, 6 months, there's this many fish. So after 1 year, there's 12 months. So population in 12 months, which is substitute T equal to 12, we solve for that, get 256 fish after 1 year. Okay, anyone has any question? It's just using this formula. And using the initial condition, I use a separable method. Then use a condition, initial conditions to get the constant values and plug in to get the population function. All right, let's keep moving. Okay, limitations on space, food supply, and other resources could reduce the rate of population growth as population growth. That would give us a population model that looks like this. dp dt equals to f of p times p of t, right? So f takes population function as the input, so composition functions, and times the population function. Well, f of p is a decreasing function of p. So one simple model to use is this. F of p equals a minus b times p. Okay. If b is a positive number, negative b is a negative number. So of course this is, you can treat this, right? Looks like negative slope, right? Decreasing function, you can think that way. So that will give us dp dt equals to f of p, which is a minus bp, p. This is ap minus bp squared. P population is a function in terms of t. Okay, p is the p of t. Well, ap is the absolute birth rate of bp squared, is the absolute death rates. Right? If you go back to the original one, the beta of t minus delta of t. So this is beta of p, beta of t. This is delta of t, right? That's why here it says AP is the absolute birth rate, BP squared is absolute death rate. or equivalently, dp dt equals some constant multiplied by m minus p times p. Just rewritten this one. All right. And use this model we call logistic equation. Okay, we call this logistic equation. Let's see an example. So solve the logistic equation dp dt equals k times m minus p times p. Well, initial condition is this, and we want m greater than p. Right? So solve this differential equation by separating variables. So dp over dt. Now we multiply dt on both sides. We divide m minus p times p on both sides, so we get this. We get this side dp over m minus pp times p. The other side is the k dt. Then we integrate both sides. Right? Integrate k, just get a kt plus a constant. Integrate this. We use partial. So how do we integrate this? Because we see we have 2 factors in the denominator. So we want to use partial fractions. Use partial fractions. Hopefully you still remember how to use partial fractions, right? Because we have 2 factors in the denominator. You know, we want to find such a over one factor, such a b over the another factor, which make this makes this. So do that, we find a equals to 1 over m, b equals to 1 over m. Okay, same thing. So integrate this, right? Get a 1 over m times both of this. So basically, you see 1 over m. So a is 1 over m. We can write it as 1 over m times m minus p. And b also equals to 1 over m. That's 1 over m times p. So we factor out 1 over m. 1 over m. So we have 1 over m minus p plus 1 over p dp. We'll integrate this. We'll get ln, because we are integrating in terms of p. In terms of p. So m just some constant. So we get ln absolute value of m minus p. We don't really need the absolute value of m minus p because m is, we define m greater than p. M greater than p. So we don't really need the absolute value sign. But then by chain rule, we have -1 from negative p. So that's why we get negative ln m minus p and plus ln p. Right, then we have 1 over m here, plus a constant. So simplify that, we get this 1 over m, ln p over m minus p, plus a constant. That's the integration of the right-hand side. Right, integration of the right-hand side, we get that. Integration of the left-hand side, we get that. Integration of the right-hand side, we get the kt plus a constant. So we have the left-hand side equals to the right-hand side. We combine those 2 constants. We write it as C3. So ln p over m minus p equals to the k, because we have this 1 over m multiplied by m on both sides. That's why we have k times m times t plus a constant. That means we have e to the power kmt plus a constant equals to this absolute value of p over m minus p. Right? We know m greater than p, but we don't know p itself. Even though maybe p can be negative. Can p be negative? We don't really measure population negatively. Anyway, you know, this absolute sign is not necessary. So this equals to, right? So this e to the C3, we can just write as constant. We use C4 to represent. So we see this solution. So it's constant multiplied by e to the kmt, right? And yes, indeed, you know, population, we don't measure negatively, so we don't really need this absolute value sign. So we have this p over m minus p equals to this, right? We want to use the initial values given. We use the initial values given. We're just treating this p naught as some number, right? So what do we have? So C4 is equals to this p naught over m minus p naught, because we're treating m as some numbers too. And then we substitute C4 into the equation, into this. But p over m minus p equals to this p naught over m minus p naught times e to the kmt. So, so note here, this is saying if p is greater than m, because the above case is m greater than p. In case if p is greater than m, then what do we have? The absolute value will be negative, right? Because m minus p will be a negative value. So the absolute value of it is negative, negative become positive. Then what do we get? In the end, we get this. Oh, same, right? Because both sides will be introduced with a negative sign. This side will have negative sign, the other side will also have a negative sign. In the end, they're the same. So either way, we get a solution like this. If we rewrite P, but I don't really like this. I don't really like this equation. I don't really like this equation. I prefer this equation. Personally, I prefer this one. This looks beautiful because there's a symmetry in here in this equation. This looks beautiful. This to my eyes just doesn't make any sense. This to my eyes just doesn't make any sense. All right. Anyone has any question? Pretty direct, right? Oh, let's see. Okay, if we solve for P from here, right? So we're trying to solve for P, then we have to go through this process. Then we move this term to the other side. Then we solve for P. So we get a P of T equals this. Okay. The population function in terms of the initial population and such M and such K, right? Because it's a function in terms of T. Notice if we take a limit when that time run into infinity, what do we get? We get the limit of the population equals to M. Equals to M. That's why we call M the carrying capacity. What does it mean, carrying capacity? It means the environment can support the maximum amount the environment can support. This is also going back to a very lower case of statistics course. If P naught, if the initial population is less than the carrying capacity, then we, of course, we have this, right? Less than M. And if the initial population is greater than the carrying capacity, that's chaotic, right? Ideally, you know, we want a balance. If we talk about a human population, you know, there is a balance. We don't want the population too low from the carrying capacity, And certainly we don't want the population to go beyond carrying capacity. Or maybe for other populations as well, for all life. Right? Okay, let's see an example. So dx dt equals 3x times 5 minus x. So we're given this equation, and we're given initial value, x of 0 equals to 8. So let's see dx over dt equals, we start with this equation, we separate variables. We have x term on one side, we have constant on the other side. If you were saying, what's the problem? I leave this 3 on the other side. That's no problem at all. We integrate both sides simultaneously. We get this equation. No, we integrate simultaneously. We get this one equals to 3t plus a constant, right? And partial fractions. There's 2 factors in the denominator. When we want to integrate, what do? We use partial fractions. And then partial fractions gives us something like this. So solve for a and b. So a and b equals 1/5. So this one we separate into 1/5, 1/x plus 1/5 minus x. Now we can integrate this. So have integrate that, we get 1/5 ln x for 1/x.
Okay, so you stop and come back. I don't understand. So how comes like a is 1/5? Oh, sorry.
Oh, that's okay.
I get lost.
Oh.
Sorry.
No, it's okay.
Because
So
you go so fast, so I don't get like a is equal 1/5. So could you repeat again?
This is a calculus 1. This is
Okay.
from your calculus 1 course. Okay, something called partial fractions. From your first course of calculus, something called partial fractions. Okay, what you do with this? How do you integrate this? Your denominator has 2 factors, so you have to split into 2 terms. So for this one, you have to split into 2 terms.
Okay.
And one term has a denominator of x, the other term has a denominator of 5 minus x.
Okay.
And you don't know a, you don't know b. You just use those 2 as variables for now.
Okay.
So when you do this, right, you need to find a and b.
Okay.
How do you find your common factor? Common denominator is 5x times 5 minus x. Then that means a, you need to multiply by 5 minus x. So the first term, you multiply 5 minus x, divide itself.
Okay, I got it. Yeah.
Your second term, you multiply by x over x, so you get this.
Okay.
Now you distribute a, you get a 5a minus ax plus bx. You get you get a 5a plus b minus ax. Because the denominator equals to each other, the forces the numerator have to be equal. So that means this numerator equals to this one.
Okay.
This numerator equals to 1. Now you compare. What's the number before x? You don't see x on the left-hand side. That means b minus a is 0. What that means, b equals to a.
Oh, okay.
And you do have a constant term. Constant term 5a equals 1. That tells you a equals 1/5.
Oh, okay. Got you. Yeah. Thank you.
Okay. That's called partial fractions.
I forgot.
Okay, that's okay. All right, so yeah, so in the end, it's just arithmetic, right? You just calculate. So once you integrate, you get this. You just calculate. Then you use calculator, you get this. Then you use the initial value, substitute in, you get the constant. Right, you get your constant equals to a over 3. You plug in a over 3 into the equation. you get this. You get x over 5 minus x equals this. Well, this is saying, but x over 5 minus x is less than 0 for t greater than 0. How do we know that? So this one has to be negative, right? So if this one is negative, this one has to be negative. Okay, let's see this, right? You see, basically x prime equals this. What is this? This is downward parabola. This is the second order polynomials. So that means the original function has to be the degree polynomial. So which means what? Which means the domain of x is going from negative infinity to positive infinity. So now let's go back to this, because I'm just asking. This is saying x divided by 5 minus x is less than 0. We can rewrite this, right? We can do, we can rewrite this as negative x over x minus 5. If we do that, because I'm just calculating why this has to be less than 0. If we do that, if we do negative x over x minus 5, then in the numerator we can do x minus 5 plus x minus 5 plus 5. Then we see we have negative 1 minus 5, negative 1 plus 5 over x minus 5. That's why this is saying this is always less than 0. It is true, always less than 0. So absolute value of it has to be negative, negative, right? Negative and negative become positive. So we get this. Then we solve for x. We try to solve for x. We try to solve for x. We get this in the end. We try to solve for x. In the end, we get x equals this. Equals 40 divided by a minus 3e to the negative 15t. All right. So that's our solution. Okay, any questions for this? This is just a lot of calculation. All right. I'm not going to spend too much time on talking about calculations. Yes, Gregory. Gregory, I cannot hear you. Are you speaking? I can't hear you.
Okay, sorry about that, Professor. Sometimes I need to reload the page.
Oh, okay. Yes.
Okay.
Now I can hear you.
Great. So my question was, when we go back to the top of the this problem,
Yeah.
it says don't use the formula we derived. What does that mean, or like what's that about?
Oh, for this question, it's just saying, don't use the previous one. Don't use the previous one. Just solve this one, just by
Okay.
itself. Yeah,
Okay.
that's what it means. Yeah. Okay, this, I guess, yes, so we're here. So this one is saying, consider population of rabbits that satisfy the logistic equation such. So that's, we derived it before. dp over dt equals AP minus BP squared, birth rate, death rate. And where we think of AP as the birth rate and BP square as the death rate. The initial population is 120 rabbits, and there are 8 births per month and 6 deaths per month at initially. So how many months does it take for the population to reach 95% of the limiting population M carrying capacity? Okay, initial population is 120. Initial birth rate 8, and which is A P naught equals to 128, which is we solve for A, that's 1/15. And the initial death rate 6, BP square, which is B, the initial P naught square, and the initial is 120. We solve for B, so B equals to 1/2400. And then we put it back into the equation, dP dt. So AP minus BP square. A is, well, let's just following this. This is in, let's factor out P. Factor out P, so the first one we have A. Let's factor out BP. Factor out BP, so we have A over B for the first term for AP, and the minus P for negative BP squared, since we factor out BP. So let the constant represent P equals to 1/2400. So M be the ratio of A to B, which is 1/15 over 1/2400. Calculate, that's 160. So we use this one we had before, right? Remember, this is a solution for such equation. So we just plug in all the numbers. So M, we use M, K is B, M carrying capacity 160. Just plug in all those values. Because what do we want to find? We want to find how many months, the time T, does it take for the population to reach 95% of the limiting population M, 0.95 M. So the population reaches 95% of the carrying capacity. Okay, so the both sides we divide by M. So we see M is gone. M here divided by M divided by M. So we have 0.95. Initial is 120. Initial is 120. Carrying capacity 160 minus 120. Then e to the power K, negative K times M times T. Simplify it, we get this. Keep simplifying. Keep doing the calculation. In the end, we get e to the negative T divided by 15 equals such number. We take ln on both sides. So negative T over 15 equals this, ln of this. And we use a calculator. What we could do T equals to ln 38 divided by 6, then multiply by 15. We use a calculator, that's about 27.69, about 28 months to reach 95% of the limiting population or the carrying capacity. Okay, anyone has any question? Skipping the calculation, so the important part is this. So this question is suppose the scenario fits into this logistic equation. Anything important in math, it has a name. So this is called a logistic equation. Then we translate, all those words into it. then to calculate. It's just a lot of calculation. And also the K and the B, K and M. K is the initial birth rate. It's the constant for the birth rate, right? Remember the initial, no, remember this represents birth rate function, AP, and BP squared, the death rate function. So such K is the B, such M is the ratio of A to B. So this two is just, and the rest is just calculation. Right. Oh, that's it for today. But I think the problem will be the homework. Let's see the homework. Let's see how many homework you do. So that's 5. That's this one. There's only 4 homework. That's why, and the 4 homework, 2 are done, right? 2 are done. Only 1, 2 is not taken. So what you can do is you can make up homework 5. Okay, you make up homework 5. You make up homework 6 by changing some numbers, by changing some scenarios. Make up homework. All right. David is saying, let's change the constants. Change the constants. Change the constants. Okay, I guess. Oh, hold on a second. Let me share with you this. Let me share with you this page. You know, because you want to present, right? Change something interesting. Maybe you can search online to see some other possible questions you can solve. Okay, be creative. All right, any questions? That's all I have to talk about for tonight. And but if you're able, keep going with the new material. Let's go back to see what's coming up. What's coming up? Differential equation, you know, class supposed to be very interesting. So 6. Let's see what's so day 6. Okay, velocity and acceleration models. So all those life models. Okay. Just a lot of calculation, and which in class, I don't want to spend too much time for calculations because I assume all of you are pretty advanced. Day 7. Okay, day 7, we're going to second order linear differential equations, all right? Okay, everything's up there, 7, 8, 9, 10, up to 22, all right. Okay, anyone has any questions? Again, I want to show you this. I want to show you the presentation grades. Let's go here. Let's go to grade center. Because some of you haven't presented once yet. So your presentation, you see, yes. Some people already presented 3 times, which is 30% of already, 30% already. And some of you haven't started yet. So why don't you just plan on starting presenting? Yeah, today will make 4. I haven't updated yet, right? Plus today will be 4. So I just want to encourage everyone, you know, try to present. All right, if the question is not enough, and of course, you know, when you form study groups, you talk to each other, You don't want to do, well, of course, you know, like Ryan, Liz, I'm sure you're able to do everything yourself. But for the rest of you, if you're struggling on presentation, struggling on homework, form study groups. If you don't have enough questions, make up some interesting questions, all right? Because when you present, you're presenting to the class, you're presenting to me, you're trying to convince me saying, Professor, you know, I deserve A or A plus for this class, all right? So show me. All right, that's all I have to talk about. Anyone else has any other questions? If not, you're a free bird for tonight. And I see you. And I see you next, oh no, I see you on Thursday. Thank you. Okay, thank you. Right, try to present, okay? Good night, everyone.
Thank
Good
you,
night.
Professor.
Thank you. Have a good night.
Good night.
Good night.
Good night.
Professor.
Yeah.